We have just 2 or 3 more little things to look at to finish this thing out. In addition to those polynomial functions that follow the power rule, we have 2 or 3 other rules that we're going to look at. And the first 2 of them I'm actually going to go through a proof to show you how we get to the result of it. You don't have to complete the proof. I don't expect you to complete the proof every time you perform that derivative. And you'll understand what I mean as soon as we start working on this. The first function that I want to look at is the sine of x. Now, before we spend a lot of time going through that one, I need you to open your books to page 81. Because that will be pretty helpful for us. There's a couple of theorems on page 81. One was the squeeze theorem that we looked at, but the next one was kind of midway down the page. It's some special theorems, special limits that we saw in chapter 1, and we're going to come back and use those when we actually prove this particular limit and this particular derivative. Again, this is a proof, and we'll show you how the pieces fit together. Now, would you agree that to set up the derivative using the limit process, it's the sine of x plus delta x minus the sine of x divided by delta x?
Yes.
Okay, that matches. You might want to put your finger in the book here and go to the back cover page for just a minute, because the next thing I actually want to do here is have the limit of delta x goes to 0, but I want to use the angle sum formula for the sine, which is the sine of x cosine of delta x plus the cosine of x sine of delta x, and then minus the sine of x all divided by delta x. And I want you to kind of remember, oh yeah, that's how we expand out that angle sum formula for the sine of the sum of 2 angles from trig class. This part right here. We need that to be successful. Okay, remember doing that from last year?
Yeah.
Some of you do, some of you don't. But there it is, and there's that formula. So I didn't just make that mess up. But the next thing we're going to look at here is so I observe some things briefly, such as right there, you'll have a sine of x and a cosine of delta x. Here is the cosine of x and sine of delta x. There really isn't anything common there. But it comes down to this term, and there is the sine of x again. So that sine of x on the end, and this sine of x cosine of delta x have the common factor. That is the common factor. So let's use that, and let's rearrange the order just a little bit. This is equal to the limit, as delta x goes to 0, the sine of x cosine of delta x minus the sine of x. In fact, I'm even going to write that as a single fraction, and I'm going to say plus the limit as delta x goes to 0 of the cosine of x sine of delta x. Alright, sine of delta x over delta x. 2 separate things. Split them out, cross the plus sign in that fraction. Any questions about that part of it? It makes a little sense, I hope.
Why do that and then separate though? Just because of a common factor?
Part of it is, yes. The other part's going to show up here. The other part's going to really show up here in a second. Okay? Right here I've got a common factor in the numerator of sine of x. So that means I've got this thing equal to the limit as delta x goes to 0 of negative times the sine of x times what's left behind here is then 1 minus the cosine of delta x over delta x, after a negative 1, or negative sign, and then plus the limit as delta x goes to 0 of the cosine of x times the fraction sine of delta x over delta x. Well, if we look back on page 81 at those special theorems, the limit as delta x goes to 0 of 1 minus cosine delta x over delta x has what limit value?
0.
So this whole term right here limits out to 0. Over here, the limit as delta x goes to 0 of sine of delta x over delta x becomes
1.
So this part turns to 1 times,
Cosine 1.
so that means, therefore, the derivative of f of x is equal to the cosine of x. In other words, if you see a sine of x and you're taking the derivative, you're going to write the derivative is
Cosine of x.
cosine of x.
Do you have to prove it like that, or is it just assumed?
So, an example, g of x equals 3 sine of x. The derivative of g of x is,
Cosine x.
this is all you have to write.
Oh, cool.
We proved it, it'll work now. It fits in your world, mathematically it works every time. So that's all you gotta do.
Wait, how to go from sine to cosine?
Because the derivative of the sine function, by that proof,
Okay.
is cosine of x.
I kind of realized that it's this.
Yeah, okay, that works.
Slip off a little bit.
Yes, sir.
Is it like similar for tangent?
Okay, now wait a minute. Time out. I'm going to talk about the cosine function in a second. And then you have to hold on to that question about the tangent, the cosecant, the cotangent, all that good stuff until later.
Oh, no.
We have to learn other rules first to correctly find those derivatives.
Getting ahead of stuff there.
So just kind of hold on. It'll be all right.
When are derivatives used in real life? Like, I honestly
Remember,
don't know.
they are telling us about rate of change of something. So whenever we have in physics light propagation or any kind of electromagnetic wave, it is a sine or cosine or tangent function. And if we want to go the rate of change of those things, we have to go to the derivative to describe that rate of change of that object. So we use it, there's other places we use it, sound waves and other things like that. So any audio technician will want to know rates of change of things. Doppler effect deals with rates of change. That's what that means. So anything we do with wave motion, rates of change with sines, cosines, and tangents, and all that good stuff. Okay? Well, that was fun.
Well, it lasted.
Let's have a little more fun. Yeah, insert your comment now. If I have the cosine function equals h of x, let's see what the derivative of the cosine function becomes. And by the way, folks, seeing as how this one is very similar to the one you just wrote down, if you wrote it down, you can just sit down with your pencils and pause and watch instead of write this down. Again, I'm not expecting you to give me the proof of this function. I want you to see how it works, to see why the answer is what it is, but I don't need you to prove it for me. So you can watch this and I might go a little faster. So the limit here is, or the derivative is the limit as the cosine of x plus delta x minus the cosine of x divided by delta x. And then we look, we have the limit as delta x approaches 0 of the cosine of x, cosine of delta x, minus sine of x, sine of delta x, minus cosine of x. Over delta x. You agree with that? Okay. Again, we're going to select like terms. This one here has a cosine. That has a cosine of x in it. And so we get the limit as delta x goes to 0 of the cosine of x times the cosine of delta x minus 1 over delta x minus the limit as delta x goes to 0 of the sine of x times the sine of delta x over delta x. Now, I didn't factor the negative 1 out of here, but its limit's still 0. Yes, ma'am?
Would the whole thing be over delta x, or would it just be cosine delta x minus 1?
They're the same thing. Because of the multiplication, it's the same thing.
Okay.
So if we can write it like that, or we can write it like that,
Okay.
it means the same thing.
Okay.
Good question. So that's 0 from that limit. This part of it right here is 1, and I'm left with the negative of the sine of x. And so therefore, the derivative h of x, h prime of x, is equal to the negative of the sine of x. So what has to happen is the derivative of the cosine function is the negative of the sine function. That's the part you really need. But it shows up and it has to do with how this angle sum formula for cosine works. That's why we get the opposite. Questions about that? Okay? I'm not going to prove this one for you. It's a fun little proof. But you don't have to do it. If I have r of x equals e to the x power, the exponential function, the derivative of the exponential function is clearly the exponential function, e to the x. It is its own derivative. One of the only functions that does that.
Why?
Okay, if you go through the proof, when you look at the proof, it shows up and becomes exactly that. It becomes itself.
You said it was one of the only proof or functions?
No, the derivative of 1 is 0.
No, you said it was one of the only functions?
Yeah, it's one of the only functions that does that.
What are the
There's
functions?
there are others.
Now you're going to make me think.